any redox cell, whether it be electrolytic or galvanic, is that there is an anode and there is a cathode. At the anode there is oxidation, at the cathode there is reduction. Whether it's electrolytic or galvanic, doesn't matter. That's the key, right? At anode is oxidation, cathode is reduction. Just get that into your heads.
Unox.
Yeah, exactly. Right. So let's look at this one. We've got copper and we've got silver. So the key to all of this is you need to figure out which one is being oxidized, which one is being reduced. And this is how we figure it out, right? So let's look. Anode, that means we have oxidation. So we have oxidation is loss of electrons, right? Then we have our cathode. We have that cathode is reduction, gain of electrons. So now we've got to figure out how we're going to figure out which one's the anode, which one's the cathode. People have been taught tricks like what is above, what is below. That messes you up because it's not, not like yours wasn't as bad. There are some people who have it like much worse one. Yeah. The key is you got to figure out legitimately which one is being oxidized, which one is being reduced. Then you can know what's the total potential. So if you look at your table of standard potentials, right? If you look at it, their reduction is the gain of electrons. So if I look at my potassium right at the top, K plus an electron becomes potassium solid. That's the equation for reduction of potassium. Make sense? So if I look at my potential back there, and I've got my reversible reaction. So I've got negative 0.294 volts. That's what I've been given, right? That means for that forward reaction, K plus E minus to K solid, that is negative 2.94 volts. That's the voltage for reduction of potassium. Make sense? Now, if I want potassium to oxidize, that's the other way. Potassium solid to K plus electron, right? Make sense? But because the reverse reaction is the same thing with any other equilibrium reaction we do, so you actually flip the voltage if you think about it. Does that make sense?
Yeah.
So if I wanted to oxidize, if I wanted to oxidize potassium solid, it would give me 2.94 volts positive, because it really wants. Does that make sense? Because I'm going the reverse reaction. That means I'm going to flip whatever voltage they've given me in that table. Does that make sense? Does that make sense to everyone?
Mm-hmm. Yep.
Right. So that's the key, right? Because think about it. Potassium really wants to be K plus. So it will give me that huge voltage, 2.94 volts, to be K plus. Again, K plus really doesn't want to be K solid. So it would take me 2.94 volts to become K solid. Right? And the key to all of this is the one that's going to happen is the one that takes the least amount of energy. Makes sense? Now, in this one galvanic cell that I've got here, I look at all the species I've got. I've got copper solid, I've got copper 2 plus in solution, I've got silver ion, and I've got silver solid, right? So now let's look at which one is going to be oxidized. Oxidation is loss of electrons, right? Of course, copper 2 plus is not going to be copper 3 plus, and Ag plus is not going to be Ag 2 plus. It's not going to happen. So if I want to look at what's being oxidized at the anode, I can cross those off. Does that make sense? Makes sense, right?
Can you go through that again just quickly?
Because now I want to figure out, this is all my species I've got, right? So I've got copper solid as my electrode, I've got copper sulfate solutions, I've got Cu2 plus.
Yeah.
Same with my silver and my silver nitrate, right? So I want to figure out which one is being oxidized.
Yeah.
Copper 2 plus is not going to be copper 3 plus, it's not going to lose another electron.
Yeah.
Same with my Ag plus, it's not going to be Ag2 plus, it's not going to lose another electron. So if I want to figure out what is losing electrons, I can cross those two off,
Okay.
right? So now I look at my two half equations on my table of potentials. I've got copper solid to Cu2 plus because copper wants to be 2 plus. Copper plus doesn't really want to be that. Copper 2 plus an electron. Plus 2 electrons, my bad. So what is the potential for this to happen? For the copper to copper 2 plus? What is it?
Negative 0.34.
Negative, right? Because oxidation. So that potential gives me there for the forward reaction, but oxidation is a negative reaction if you think about it. It's loss of electron. So it's copper solid to copper 2 plus. That's negative 0.34 volts. Does that make sense to everyone?
Yep.
Negative 0.34. Now let's look at my Ag solid. Ag solid to Ag plus an electron. What's my potential for that?
Minus 0.8.
Negative 0.8 volts. Because it's the reverse reaction of what's even in the table, right? That's the key part. So this reaction will take me negative 0.80 volts. This one is negative 0.34 volts. Which one's going to happen?
Copper.
Because they're negative, right? So this means it's taking up energy. That one takes up less energy than this one. That copper to copper 2 plus is the one that's going to happen preferentially to this one. Does that make sense? Does that make sense? Make sense?
Yeah.
Jello, does that make sense?
Or you can think, can I hit? If you prefer, since the reduction table is the lower you go, the more likely the more it wants to reduce, right? Because it's
That's
high
the thing.
voltage.
That's the thing, right?
It's a reduction potential for a reason.
I don't like thinking like that because it's kind of not really the chemistry. Because this works whether it's reduction, whether it's galvanic.
It's just a shortcut. It's just a shortcut.
Because when you get electrolytic cells, you do the exact same process. But then above and below can stuff up if it's an electrolytic cell. So I like to do this.
Wait, so what's the difference in the electrolytic cell?
It's exactly the same. It's just that when you add the total potentials,
It's not.
you can do what you want, but this is the thing, like, I'm trying to say what is the way I do things. So I think this is the chemically correct version. That's why I like to do this, right? So the next,
His way stuff up again.
It doesn't stop up.
No, in electrolytic cells, how does
No, like-
this way stuff up?
maybe not the method, but in your head, like, you're trying to figure out which one is above and below. Like, so it's up to you. Like, if you've already learned that really quite solidly, that's up to you. Right, so the next one we've got to figure out is we've got to figure out what's happening at the cathode, what is being reduced, right? So at the same process, my Cu solid is not going to be Cu minus, my Ag solid is not going to be Ag minus. Does that make sense? Right, so if what's being reduced, I have Cu2 plus, and I have Ag plus, right? So my two half equations of that, Cu2 plus 2 electrons, becomes Cu solid, Ag plus an electron, becomes Ag solid. So what's my potential for these two?
Positive 0.3 for copper, positive 0.8 for silver.
Which one's going to happen?
Silver.
This will give me this much energy if this happens. This wants to happen more than my Cu2 plus wants to be reduced. This is going to happen at my cathode. Does that make sense? So that means now I have my two half equations. My copper solid is going to be oxidized at that point. At my cathode, this is going to be reduced. Does that make sense? It's a process of figuring out which one's going to happen based on which one requires more or less energy. And that will be exactly the same process for my electrolytic cell. So now I look at my anode equation. So my anode equation is copper solid to Cu2 plus 2 electrons. And here I've got Ag plus an electron becomes Ag solid, right? Yep. Negative 0.34 volts, 0.80 volts. So what is my total voltage for this galvanic cell? 0.46. Because if at one half I've got at my anode it's taking me 0.34 volts for that reaction to happen, and my cathode is giving me 0.80 volt. So logically my total voltage for that galvanic cell, I just add the two. Does that make sense? 0.46 volts. Does this make sense?
Yes.
So this is what you do for any electrolytic cell, whether it's your galvanic or your electrolytic. Figure out at my anode, what is being oxidized, right? I've got all my species up here, copper solid, I've got my Ag solid. Then I figure out which one is going to take less energy. This one is negative 0.34, this one's negative 0.80 volts. This is going to take more energy to happen than that one. That one's going to happen. At my cathode, I look at my two, this one wants to happen more than this one wants to happen. Therefore I'm going to circle my Ag plus being reduced as this one's going to happen. This makes sense?
Yeah.
So now my total cell voltage, 0.46 volts for this galvanic cell. Make sense?
Yeah.
So now I'm going to do electrolytic cell, and you'll see that it's the exact same process. So that's why I like to do this, because it kind of, you don't, like, once you understand it, all the questions make sense, because you understand the core concept and what's working on the question.